natural silk fiber, and silk fibroin materials, composition, processing, and applications. Natural silk fiber, derived primarily from the cocoon of the domesticated silkworm Bombyx mori, represents one of the oldest and most versatile biopolymers known to humanity. Its exceptional mechanical strength, biocompatibility, and hierarchical structure have driven extensive use in textiles and, more recently, in advanced materials science and biomedical engineering. This video reviews the historical development of sericulture, the chemical composition of natural silk, methods of harvesting and processing, and places particular emphasis on silk fibroin, SF, its molecular structure, extraction, regeneration, and diverse applications. While spider silk and synthetic silk analogues remain active areas of research, the focus here is exclusively on silkworm-derived fibroin as a scalable and industrially relevant biomaterial. Introduction and historical perspective. Silk has played a central role in human civilization for millennia. Historical records and archaeological findings suggest that silk production in ancient China dates back over 4,000 years, with some evidence indicating even earlier use. Traditional narratives attribute the discovery of silk to Leizu, also known as Xiling Shi, who is said to have recognized the unraveling of silkworm cocoons into fine filaments. The development of sericulture, the cultivation of silkworms for silk production, became a closely guarded technological advancement. It contributed significantly to the establishment of transcontinental trade routes such as the Silk Road. Over time, silk evolved from a luxury commodity into a material of scientific and technological interest due to its unique structural and functional properties. Chemical composition of natural silk fiber. Natural silk fiber from Bombyx mori consists primarily of two protein components: silk fibroin, SF, approximately 70 to 80%, Sericin, SR, approximately 20 to 30%. Minor constituents: waxes, pigments, and inorganic salts. Fibrous protein characteristics. Silk fibroin belongs to the class of fibrous proteins, characterized by repetitive amino acid sequences that promote ordered secondary structures. Unlike globular proteins, fibrous proteins such as fibroin, collagen, and keratin derive their mechanical properties from intermolecular interactions, including hydrogen bonding and van der Waals forces. Amino acid composition. A limited set of amino acids dominates the primary structure of silk fibroin: glycine, approximately 46%, alanine, approximately 30%, serine, approximately 12%, tyrosine, approximately 5%. These residues form highly repetitive motifs which facilitate tight molecular packing and beta sheet crystallization. Structure and hierarchical organization of silk fibroin. Silk fibroin exhibits a complex hierarchical structure. Molecular architecture. SF consists of a heavy chain, H chain, approximately 350 kilodaltons, a light chain, L chain, approximately 25 kilodaltons, linked via disulfide bonds, and a glycoprotein P25, approximately 27 kilodaltons. These components assemble in a 6:6:1 ratio to form the fundamental structural unit. Secondary and tertiary structures. Silk fibroin adopts multiple conformations. Silk 1, metastable, water-rich, alpha helix/random coil. Silk 2, stable, beta sheet-rich crystalline structure. Silk 3, interfacial triple helix structure, less common. The beta sheet nanocrystallites embedded in an amorphous matrix are responsible for the remarkable combination of strength, elasticity, and toughness. Harvesting and processing of natural silk. Sericulture and cocoon production. Silk is harvested from the cocoons spun by the larvae of Bombyx mori, which feed primarily on mulberry leaves. During cocoon formation, two fibroin filaments are extruded and bonded by sericin, forming a continuous fiber. Degumming process. Sericin removal. Raw silk fibers are stiff due to the presence of sericin. Degumming is performed to isolate fibroin. Conventional method: boiling in sodium carbonate, Na2CO3 solution. Alternative methods: enzymatic treatment, microwave-assisted degumming. Proper control of degumming conditions is critical to preserve fibroin molecular weight and mechanical integrity. Preparation and regeneration of silk fibroin. Dissolution of fibroin. Degummed silk fibers are dissolved using chaotropic agents such as lithium bromide, calcium chloride ethanol water systems, Ajisawa's reagent, and zinc chloride. The resulting solution is dialyzed to remove salts, yielding an aqueous fibro-in solution. Regeneration into functional materials. The aqueous SF solution can be processed into various material forms by controlling conformational transitions. Silk 1 materials, obtained via slow drying or controlled annealing. Silk 2 materials, induced by alcohol treatment, heat, or water vapor annealing. Silk fibroin-based materials and fabrication techniques. Films. Fabricated via casting, spin coating, or printing techniques. SF films exhibit high optical transparency, greater than 90%, excellent mechanical flexibility. SF films have applications in wound dressings, flexible electronics, and optical devices. Fibers. Advanced spinning methods, wet spinning, electrospinning, microfluidics, enable controlled fiber diameter and alignment. SF fibers are used in sutures, tissue scaffolds, and load-bearing treatment materials. Hydrogels. SF hydrogels form through beta sheet cross-linking and can be tuned via pH, temperature, shear, or ultrasonication. Applications in tissue engineering, bioelectronics, and drug delivery. Three-dimensional, 3D scaffolds. Porous SF structures fabricated by freeze-drying or foaming provide high porosity and an interconnected network. Suitable environments for cell growth and tissue regeneration. Nanoparticles and composites. SF can be engineered into micro or nanoparticles for controlled drug delivery, reinforcement in composite biomaterials, composites with polymers such as PVA, chitosan, or inorganic fillers, for instance, hydroxyapatite, graphene, enhance mechanical, electrical, and biological performance. Biocompatibility and biomedical applications. Silk fibroin exhibits low immunogenicity, biodegradability, and excellent cytocompatibility. These properties make it suitable for tissue engineering scaffolds, regenerative medicine, drug delivery systems, medical devices such as sutures and implants. Importantly, the removal of sericin significantly reduces inflammatory responses, improving the safety profile of SF-based materials. Emerging research directions. While silkworm-derived fibroin remains the most scalable and industrially viable source of silk, ongoing research explores spider silk proteins with superior mechanical properties, recombinant and synthetic silk analogs, bio-inspired silk-based hybrid materials. However, challenges in large-scale production and reproducibility continue to limit their widespread adoption compared to Bombyx mori fibroin. In conclusion, natural silk fiber from silkworm cocoons represents a unique convergence of biological precision and materials engineering. Silk fibroin as its chief structural component, offers a versatile platform for designing advanced materials with tunable mechanical, chemical, and biological properties. The ability to process fibroin into diverse morphologies, films, fibers, hydrogels, and 3D scaffolds has positioned it as a cornerstone material in modern biomaterials science. In the future, sustainable processing and functional modification of silk fibroin will further expand its role in high-performance and biomedical applications.